Hi, my name is Mohammed Suhail and welcome to our presentation on light field neural rendering, a new image-based rendering method for novel view synthesis. Novel view synthesis is a task of rendering a scene from unseen viewpoints given a collection of input images. Recently, Neural Radiance Field, or NeRF, achieved great progress towards photorealistic view synthesis by representing a scene using a neural network that takes a 5D input to predict color and opacity. NeRF, however, is challenged when rendering scenes with complex view-dependent effects, such as a reflection on the CD as shown here. Follow-up work such as NEX have strived to overcome this limitation. While they show improvement in some cases, their method fails to reconstruct severe non-Lambertian effects, such as refractions through liquid as shown in the example here. Our method is faithfully able to render such complex effects in either scenes where prior methods fail. Our method relies on light field to represent a scene. Light fields are vector functions on the space of oriented lines that associate a ray to a radiance value. While the light field representation can be used to directly learn a mapping from a Fourier tuple to color, such a model will produce low-quality renderings as shown here. This observation can be attributed to the fact that light fields do not have any inherent notion of multi-view consistency. To address this limitation of the representation, we propose to incorporate a geometric bias into the rendering framework, in the form of epipolar constraint. In more detail, given a target ray from a target image we wish to render, we first compute its light field coordinates. We then sample points along the epipolar lines in the reference image and extract features from them. The target ray representation, along with the features of the epipolar points, are fed into a feature aggregator that summarizes the features along the epipolar line. These features, along with the target ray encoding, act as input to the view feature aggregator that outputs a single feature vector from which we predict the color. At the core of the epipolar feature aggregator is the epipolar feature transformer. The purpose of this transformer is to reason about correspondences in the reference views to aggregate features of points along the epipolar line. Given the target ray representation and the epipolar point features, we first concatenate them to form a sequence that acts as input to the transformer. The refined features from the output of the transformer are used to estimate pairwise attention weights between each epipolar point and the target ray. These weights, denoted by alpha, are then used to obtain a weighted sum of the epipolar features. Here, we show a visualization of the weights estimated by the network for 4 target pixels in the Lego scene. As shown by the green circles, the highest weights are attributed to the points that correspond to the target pixel. Similarly, at the core of the view feature aggregator is the view feature transformer. The purpose of the view feature transformer is to reason about occlusions and aggregate features from multiple reference views. This module takes as input the aggregated features from each epipolar line to estimate a pairwise attention weight for each view with respect to the target ray. Visualizing the attention weights beta show the occlusion reasoning capability of the model. Here, we show an example of image rendered from the chair scene with the corresponding weights beta of the 3 views represented as RGB channels. We observe that when rendering the cushion, the model gives higher weight to the reference view in which the region is mostly visible. Similarly, when rendering the back of the chair, the model devotes equal attention to views in which the regions are equally visible. We perform experiments on various datasets to measure the efficacy of our model. On the RFF dataset, we compare against previous state-of-the-art methods such as NeRF and NEX and show superior performance across all metrics. On the left, we show a rendering produced by our model on the room scene. Similarly, on the Blender dataset, we outperform prior work such as MIP-NeRF. Finally, on the Shiny dataset, our model achieves new state-of-the-art results. Our model's ability to reconstruct such complex view-dependent effects can be attributed to the attention-based aggregation mechanism that chooses to either interpolate colors and features from reference views or directly predict it from light field coordinates. For more details, results, and code, please visit our project webpage. Thank you.